Good afternoon. This is CIVE632, Computational Hydraulics and Hydrology. Today is Wednesday, October 6, 2021. And the subject is diffusion waves, still diffusion waves. You see the syllabus, and today we're going to cover D12, D13, 14, 15, and 16. If we don't get to 16, we'll spill it over to the following week or whenever we get around to it after the exam. I added 12 today because I felt that I was going to be talking about general dimensionless unit hydrograph, and some of you may not have taken my class last year, so I had to kind of put everybody on the same page. So I'm going to ask you to read D12. I'm not going to touch upon D12 because it's not part of this class, but I put it in there for you to read it and be informed of what we're talking about here. I'm just going to spend 5 minutes on it. I explained the synthetic unit hydrographs because it is confusing. The whole subject of unit hydrographs is confusing. I remember one of our students asked me one day, he said he had been asked at work, and he said people were confused about the synthetic unit hydrographs, and he wanted me to do something about it. So I sat down to write this paper. It's a simple paper. It's a paper to be read, not to be published. Published on my website, but so we have in here, what is the definition of the unit hydrograph? It's a unit hydrograph for a unit effective rainfall in a unit duration. So the important thing here is the fact that the duration is a unit, not that the hydrograph is a unit, or the unit is in inches or in centimeters, but not the intensity. The intensity could be not unit. So that's a unit hydrograph. So that's because it's kind of confusing. And the unit hydrograph embodies the diffusion properties of a basin. That is why Sherman, presumed to be the gentleman that developed the unit hydrograph in 1932, that's the first reference that we have of that. That's what he wanted to do. He wanted to put some diffusion into the calculations because he knew that the rational method was not allowing or not accounting for the diffusion. So that's what he did, and he did a great job, of course, and we've been using the unit hydrograph since 1932, so that's almost 90 years. It's a good concept. It has not been superseded by the overland flow method, and we already discussed that. When they apply, one or the other applies. Okay, so runoff diffusion is calculated by means of the unit hydrograph. So how many now, the synthetic unit hydrographs are the ones that are generated from data. The actual unit hydrographs measured are very, very small number. I would say less than 1 in 100. So most of the uses, 99%, more than 99% of the uses of unit hydrographs are synthetic. So in synthetic unit hydrograph is where the importance is. So the synthetic unit hydrographs have various types. Snyder was the first gentleman who come up with a synthetic unit hydrograph in 1937. That synthetic unit hydrograph is used by the Army Corps of Engineers. Then NRCS, which used to be SCS, Marcus in particular, followed suit, and he developed the SCS synthetic unit hydrograph in 1954, which kind of parallels Snyder's, with the difference that Snyder's was designed for larger basins with more diffusion, while SCS is designed for smaller basins. So as it turns out in practice, the SCS unit hydrograph is used for small basins, and the Snyder hydrograph is used for large basins, which is cool because SCS deals with projects in the uplands where the basins are small, typically less than 10 square miles, while the Army Corps deals with flooding in the lowlands or in the valleys where the basin's size may be 500 square miles or even 1,000. So Snyder is more indicated for a large basin such as those that the Army Corps of Engineers works with. So those are mostly the distinction is that the Snyder method has more diffusion, more runoff diffusion. Okay, now The USBR, those are, I put them in there only for completeness because I would think that USBR hydrographs are used only by USBR. And they're kind of unnecessarily complicated. And if you're interested, you can go to my book, chapter 14 of my blue book. I explain in detail with examples the USBR unit hydrograph, the bioreclamation. And finally, the last synthetic unit hydrograph is the general dimensionless unit hydrograph, which I'm going to come up with, which is based on the Cascade linear reservoirs. So this is what we're going to be talking today about the Cascade linear reservoirs. Okay, so the Cascade. So the subject today is a general dimensionless unit hydrograph. I should tell you the story of this paper. Starting in the year 2003, I think I already told you this, but it bears repeating, that I started to publish only on the web. And I have a record maybe of 52 pages on magazines or journals, starting in 1977 all the way to 2003. So you have in there 26 years of publication. And then since 2003, we published, well, maybe 100, no, not 100, maybe 80 or 90. And these papers are lighter because, for the simple reason that I don't have to ask anyone permission to publish. So they're light. They're as heavy as I want them to make. I want to make them, okay? So this one is one that we published in the year 2009. The history of this paper is an interesting paper. The way I work is that I have ideas, okay, and I've had many ideas. And if I have an idea, then I kind of don't like to do it on my own. So I wait until a suitable student comes around and says, hey, I would like to get involved in this. And I've had many experiences with students. So I would say at least 20 or 30 over the last 30 years. And so in 2009, I had a small class of computational hydraulics. I think there were 4. And there was one gentleman that everybody needs a project, right? And so I give him a choice of projects, and I suggested to this gentleman that he should do this because it hadn't been done, what I'm going to discuss today. And I knew, of course, that there was a possibility for failure because the students, they're beginning, they sometimes don't know, and so on and so forth. So he tried very hard. He was a good gentleman. He tried very hard. I saw him working on it, but he failed. He couldn't do it. So then at the end of May, he came to me and he says, well, Professor Ponce, I cannot figure out what exactly is going on. I said, oh, okay, fine. And I wasn't mad at all because I figured it was a tough project. I gave him a tough project just to make sure how far he could get. So then I said, well, we need to get this thing done, might as well do it. So I sat down for about a week. So my time after a week, and it kind of, the date is almost exact because around May 8th is when classes, you guys are supposed to present your projects. So in May 15th, I wrote this thing. I finished writing this thing. So what I did is I took the hydrographs, the Cascade linear reservoirs method that had been explained in the previous paper that we just finished reading last Monday, and generalize that. And I knew that it could be generalized. It's just a matter of sitting down to think about it, and you got to have some experience. So this is the example. I'm going to spend 20 minutes on this paper because we have other things to do. Okay, so this is a general dimensionless unit hydrograph. If you think it's fast, well, so be it. The material is there. Okay, so we have an introduction in here. It's a hydrograph. A unit hydrograph is a hydrograph for a unit depth of effective rainfall, applicable to a given basin for a given duration. So what we did in here is this: by generalizing and by making it dimensionless, we took out the problem with the duration and with the area. So in the past, you had to tell a duration and you had to tell an area. Now, not anymore. Area and duration were taken out. And the only thing that is input to these basins are the amount of runoff diffusion, which is what you need. And that's given by the 2 parameters of the Cascade linear reservoirs, meaning the Courant number and the number of reservoirs. So here we talk about the theory of linear reservoirs. And we need to understand here that the T sub R has to be equal to the delta T because that's the way it's operated in the unit hydrograph world. The delta T of the hydrograph has to be the same as the T sub R of the hydrograph. Otherwise, it doesn't work. If you try to do anything else, it won't work. You get a nice answer, but it will not be the right answer. Okay, so therefore, these formulas are designed to remind us of the linear reservoir because we already covered it. We covered it in the previous paper. The Cascade linear reservoirs we already covered also in the previous paper. The Cascade linear reservoirs, the CLR, is a hydrologic model that uses a number of linear reservoirs in series in order to provide a wide range of possibilities for runoff diffusion. Runoff diffusion is what we're interested in here. Associated peak outflow attenuation and time lag. Okay, in the cascade, the outflow from the first reservoir is the inflow to the second, the outflow from the second is the inflow to the third, and so on and so forth. Typically, the number of reservoirs are chosen between 1 and 10. 1 is hardly any diffusion, and 10 is quite a lot of diffusion. Okay, once CNN are defined, the CLR method provides a unique amount of runoff diffusion, a unique unit hydrograph peak and associated time lag. What I did not know at the time, I had a suspicion, but I really didn't know for sure, is that there's a lot of similarities between the convolution theory and the Cascade of linear reservoirs. As a matter of fact, they're one and the same, and I'll show you later that that is a fact. You can start with the Cascade and get an answer. You start with the convolution and get the same answer with the same data. How does that happen? I'm not quite sure exactly because I never got deeply into the analytical math that Nash works with, Professor Nash. But the fact of the matter is, it doesn't matter. We showed beyond any doubt that these two methods are one and the same. So we have in here now to dimensionalize. You gotta dimensionalize it correctly, right? You don't want to do the Ferric deal where he didn't do it. So we need to specify that T star, which is a T dimensionless time, is the time of the TR. That's the duration. The TR is the fundamental parameter of the unit hydrograph. So that's got to be in there. The dimensionless discharge is Q star equal to Q over Q max, where Q max equal to IA, the intensity times the area of the rational method, right? That's the maximum. Remember I told you Monday that when C is equal to 2, Courant number equal to 2, and the number of reservoirs equal to 1, then we get the response of the hydrograph is the rational method, because that's the way it should be. Okay, that is the isosceles triangle of the rational method. So according to the runoff concentration principle, the Q max equal to IA, that's the runoff concentration principle. You can go back and review my book. And I is the effective rainfall intensity, and A, the drainage basin. So the Q star is equal to Q over IA. So you can see now the pattern of non-dimensionalization that is coming up here. I'm not going to dwell on the details because we just don't have the time. But if you want to get into this, deals make sure that it all makes sense. If it, God forbid, there's a mistake in there, you let me know immediately. I don't think so because we've been working with these papers for a long time, since 2009. Okay, so we have an online version of the CLR. Okay, so now I'm gonna work in here and I'm gonna show you how this stuff works. Basin area, let's say 100 kilometers. Unit hydrograph duration, say 1 hour. Storage constant, 2 hours. Got to be greater than unit hydrograph duration. And number of reservoirs, 5. Okay, and here we get this is the dimensionless unit. The unit the outflow in the dimensionless unit dimensionless outflow. Dimensionless time and dimensionless outflow. And these numbers in here, 999, are going to be repeated throughout in all the calculators that I'm going to show you tonight. So that's the calculated for the first calculation that we're doing here now. Uh-oh, I messed up. Okay, we're here. Let me go over here. Okay, good. So So now we're going from there to the general dimensionless unit hydrograph. A general dimensionless unit hydrograph can be generated using the CLR method for a basin of drainage A, a unit hydrograph duration T sub R. That means we take the area and the T sub R out of the problem. We get one hydrograph. As a matter of fact, I should say at this point, and I'm going to repeat it later on, that this is the only, out of the 5 methods that I mentioned, Snyder, SCS, USBR, 4 methods, 3 methods. This would be the fourth. This would be the Cascade linear reservoirs, generalized dimensionless. This one is of global applicability. Global means around the world, because independent of the area, independent of the duration, it all depends on some numbers, the CNN numbers, which is a way of applying a certain amount of round of diffusion. How much? Oh, that's a question that we will answer later on. Okay, so so now we run through these equations in here, and we go to the procedure. Well, no, wait a second. Then we finally get over here. It says an online version of the generalized dimensionless unit hydrograph is a function of CNN is given an online general unit hydrograph cascade. So in here, for a Courant number equal to, what do you want to be? 1, and the number of reservoirs, 5. No, 0.5. 0.5 was the one that we just did, because we did a K delta T equal to 1 and K equal to 2, I think. At any rate, this is just to show a calculation. I believe we're gonna have the 9s in here, right? It's the same hydrograph. Can you see 999 in there? It's the same hydrograph I just calculated. Only that now is coming up with only the dimensionless, the CLR dimensionless unit hydrograph. Okay. Oh, geez, I'm messing up in here. I don't want to do that. Okay, I'll go back in here. Okay, so that's one calculator. The other calculator is GDUH is a function of C in the range 0.1 to 20. In C, what did we have in here for C? I think we had 0.5. Recommended range between 0.1 and 2, correct. So we get all the unit hydrographs. These are all the unit hydrographs. Remember that for 5, you remember that it had a bunch of 9s at the peak over here. 9, 9, 9, 9, 9. They're right there. So we are actually going from a simple solution to a more general solution that covers a lot more data, but the answers are the same. The answers are consistent with what we've done, with what we have done. We have now the dimensionless time for various n values, number of reservoirs. And as you can see, with 10 reservoirs, we have more diffusion. Over here is 0.09, the peak for 5, but the peak for 10 is 0.06. Yeah, 9876. So it's more diffusion, more diffusive. Okay, so that's, let me go back in here. I should have fixed this, but I didn't. Okay, so no problem. We can just get back very quickly over there. And over here, and now finally I decided that I was going to do the whole thing, because I already done partial solutions. Now I'm going to do the whole thing. So in here, you don't put any number. It does a calculation for everything. So you can analyze the diffusion, and that's it. It does a calculation for everything. The summary table, the number of linear reservoirs from 1 to 10, the Courant number from 2 to 0.1, right, that established range, and the peak flow and the time to peak, okay? And then the dimensionless discharge for Courant number 2, for Courant number 1.5, and so on and so forth. Dimensionless time and dimensionless discharge. So this is the entire thing, the entire range of unit hydrographs, cascade or linear reservoirs unit hydrographs that could be generated for the given range, of course. You can choose something in the middle and do your own calculation. You won't do the stable, because the stable is set for only 6 values: 2, 1.5, 1, 0.5, 0.25, no, 0.2, and 0.1. Okay, so that's the general Okay, so the procedure. The procedure is like this. The procedure to derive a unit hydrograph basis in GDUH is the following. Determine the basin area. Determine the unit hydrograph interval. Run online all series UH Cascade to choose among a pair of 6 predetermined C values in N1 to 10 applicable to the basin. So you got to have some experience as to what could be the diffusion. If you don't have experience, then you will gain the experience eventually. Like the Brazilians, they use the Randazar model. They know exactly how many reservoirs and how many, and what was the Current number. That is, they call it TS, T sub S. But that was their surrogate for the Current number. After a few tries, then you know where you are. And I'll explain that in more detail later on. Okay? So run the online all series UH Cascade. If necessary, run online series UH Cascade. And if necessary, run online general UH Cascade. Okay. Now, either the convolution or the CLR method can be used to calculate the composite, because once you have the unit hydrograph, that's not the end of it. The unit hydrograph is the brick that allows you to come up with the building. And you are interested in the building, not the brick. Therefore, you need to do the convolution. So we here recommend, actually, you could do it both ways. You could use the convolution or the cascade. And it's so and behold, like I said, lo and behold, the composite flow hydrographs calculated by both methods, as long as they're tied through the Current number in the end, they're almost exactly the same. That was a discovery at the time. I didn't know that this, I thought that these two methods, convolution and the cascade, were totally different. It's a matter of which they're not. It's a matter of fact, they're like two sides of the same coin. You turn the coin into the same coin. Okay. As a matter of fact, when I wrote my book in 1986, 87, I was going to emphasize scale. I was going to say small scale, mid-size scale, large scale. Okay. So in the small scale, I put the rational method in there because our objective was floods. That's floods, because floods is a lot of the objective in civil engineering, by the way. Not all of it. There's a lot of other objectives, but flood is important. There's a lot of money into flood protection. Therefore, there's a lot of people working in flood protection. So then, chapter 4 was small basin. Chapter 5 was mid-sized basin. And then I wrote chapter 6 and 7, which is statistics. I had to put in there the statistics. Because if I didn't, people were going to say, where's the statistics? Because people still use statistics in hydrology, a whole lot. Even though, as many people have already realized, the data has lost its pristine character. Somebody said that. I love that statement. The data has lost its pristine character. What does that mean? That means in the 30 years, we threw a monkey wrench into the system, and now the data, the recorded data, is not as good as it used to be anyway, when we didn't have global warming, right? You know what I'm talking. But at any rate, I had to put in there the statistics because, like I said, I could not be criticized for not doing it. You have to react to what people say, actually. You're not totally free in this world. You wish you, but you're not. Okay, then chapter 8, 9, and 10, I was going to do the routing because that's my field, right? I'm a router guy. So I was going to split it into 3. Instead of putting one chapter, since this was a lot of material, I was going to put it into 3 chapters. So in chapter 8, I put reservoir routing. In chapter 9, channel routing. And in chapter 10, I was going to put, I put watershed routing or catchment routing or basin routing. And then in each chapter, you had to choose the methods that you were going to detail in the chapters. And I had to choose 3 or 4 maximum. I couldn't do what other colleagues had done, put 15 methods. No good. That's an encyclopedia. That's not going to sell. People want the cookbook stuff, at least for the undergrad, right? So then I was in Europe at the time. And luckily I was in Europe. And I was meeting with some friends, students of mine, former students, that had somehow housed me out there. It was in Portugal, actually. I spent two and a half months in Portugal, writing the book, hiding from everybody. That's the way you got to do it. Otherwise, you can't. And too many interruptions, right? So I talked to this gentleman who was my student, and I said, I'm writing the Cascade. I'm sorry, I'm writing the catchment method. And then he said something like, you should put in there the Cascade. We use it here. And he was also using another method I'm not exactly remember at this point. But he suggested that I should not miss the Cascade in the method. So I said, okay, fine. Catchment routing, Cascade, and did the Cascade. Now, to do the Cascade, what you need to do is to go back to SAR, right? And go back to Tang and go back to those that did it. And the SAR is a mess because they got the wrong equation. And I'm asking you to straighten it all out and take that equation and come up with our equation, or vice versa. Take our equation and come up with that equation and show, in fact, that arithmetically, or I guess algebraically, they are the same. They're the same equations. Why Don Newton did what he did, I do not know. My only speculation is that he was, I mean, he's already dead, obviously. I saw him when he was an old man, maybe 40 years ago. That they were not too comfortable with the numerics, and they were just beginning to do the numerics, and they didn't see the whole thing as we see it now, 50 years later. Okay, so then in that book I wrote the Cascade, but I had to unravel it. That's what I always do. I unraveled the Vedernikov, I unraveled the S-curve, and I was going to unravel the Cascade, and I sure did. If you read my presentation of the Cascade of linear reservoirs in my book, it will take you an hour to figure it out. And if you read it in any other book, it will take you 5 hours. That is my estimation, because they make it complex, and it's really that it isn't that complex. I tell you, I have received many comments from people exactly saying that. Ponce, you resolve the Cascade readily in your book. I couldn't read it. I mean, I couldn't understand it when I read it somewhere else. And that's correct. Okay, so I wrote the Cascade in there, fully thinking at the time that the Cascade and the unit hydrograph of Sherman were totally different things. The unit hydrograph was in chapter 5, the Cascade was in chapter 10. Totally divorced, right? That's different. It's not correct. No. In retrospect, the Cascade, I had to do something. I would have had to do something. Put the Cascade in chapter 5, or put the unit hydrograph in chapter 10, or just write a statement that says, you know, these methods look different, but they are the same. But don't forget that we learned that in the year 2009, and I wrote the book in the year 1989. So that was how many years? 20 years later, okay? So advantages and disadvantages. The GDUH has the following advantages. The procedure is global, applicable anywhere, and solely a function of CNN. Let me say this, because it needs to be said. When this thing did not exist 20, 30 years ago, and people had to come up with unit hydrographs, and they didn't like moccasins, nor did they like the other gentleman from the Army Corps, they would hire a hydrologist of reputation, of course, to tell them what to do. Like, let's say, for an example, Pima County, because I'm familiar with Pima County. Pima County, Arizona, would pick up a hydrologist or have an RFP to do the calculation of this unit hydrograph, of this particular basin. And they will pay a certain amount of money, a contract, to some hydrologist that had a reputable career in unit hydrograph calculations to tell them what it was. That's cool at the time. That was 30 years ago. But anymore now we have a global way of doing it. But you still have to do the CNN. I mean, it's not perfect. You got to do CNN. But there is some geomorphological indications as to what the CNN should be, as I will get there. Okay, the procedure is global. Unlike other established unit hydrograph procedures, such as NRCS, the GDUH is a two-parameter model, like the Snyder model. Therefore, it is able to simulate a wider range of runoff diffusion. So it has a broader range. You can tweak the GDUH a lot farther and a lot better than you would the NRCS. NRCS is a very constrained methodology. Now, everybody uses it. And I would say that if they're using it for the large basin or for a mild basin, they're wrong, they're off. And we have experience with that. We had a professor, one of my friends over at Clemson, I think it was, who commissioned a student to determine the peak rate factor of the unit hydrograph for this particular basin in North Carolina. And she came up with a value of 200 when in fact Marcus had recommended that it be 484. That's in my book, chapter 5. 200, 484, that's 40% of the value. Why? Because they were working in flat areas, and in flat areas, the SCS doesn't work. SCS works in upland when there's slopes. All you need is more than 1% and you got SCS. But if you have 0.01% or 0.001, you're dead. SCS doesn't work. Okay, so conclusions. General dimensionless unit hydrograph based on the Cascade is formulated and calculated online. We have 5 calculators to do this, or actually 4, I think. The GDUH is shown to be solely a function of the Current number and the number of linear reservoirs. Since it's independent of the basin drainage area, it is applicable on a global basis. This method calculates runoff diffusion in general. Later on, you put your area, you put your stuff in there, and it'll do it. Each GDUH is related only to the basin prevailing runoff diffusion properties. The latter is a function of the general topographic relief. With more relief, less diffusion, and less relief, more diffusion. The model's 2-parameter feature provides increased flexibility for simulating a wide range of diffusion effects. Research into the estimation of CNN. Okay, so we get there. We'll get there. I have to come back in here now. Subsequently to, oh, this one worked. I must have had the right link. Subsequently to doing this, I realized that now I had a can of worms. I had to put the genie back into the bottle, as they say. I had opened up a can of worms. We got these 2 methods. Okay, which one is better? So I said, well, I have a hunch that they're kind of, I tried anyway. I said, I'm going to work on it. I'm going to solve a problem, and then I'm going to solve the other problem with the same data and see what happens. If they get a different answer, I will call it hydrology. Hydrology can have a 30% error and nobody blinks an eye. That's true, by the way. Remember that. Professor Ponce said that, although I didn't write it in my book. Okay, you can have the Snyder method. You can have this. You can now in evapotranspiration. You can have 100% in error. Thorne White is typically low. Penman is generally high. A lot of people use Thorne White because it's easy. Penman is hard. You gotta know your stuff if you apply Penman. But Thorne White is easy. So most people use Thorne White, but Thorne White is wrong. It's off the bat. It's an empirical procedure that was developed by Thorne White, I believe in Wisconsin somewhere. I don't know. And everybody knows that Thorne White is not that good, but everybody uses it. Not everybody, but a lot of people use Thorne White. So here, now we go to the second paper. Cascade. The method of Cascade and unit hydrograph convolution are shown to be one and the same when the Cascade parameters are used to calculate the unit hydrograph of the convolution. So there's a if and but in there, a condition, a caveat. In the absence of gauge data, the Cascade parameters may be estimated based on geomorphology. Remember I said geomorphology was the ultimate answer to all our hydrologic problems. If you know the geomorphology, you can get the hydrology. That's the way it should be, because the hydrology is the flow on the terrain, and the terrain is steep. You're not going to have any diffusion. How steep? More than 1%? Forget it. It becomes kinematic. Less than 1%, well, now it can become diffusive, and then you figure out how diffusive it's going to be. And actually, the calculation that we do is all a matter of how much diffusion. That's what we're calculating, because we're combining all these hydrographs and expressing them downstream. And some of them have diffusion, some of them don't have diffusion, but by the time they are expressed together in a time and space fashion, You got to connect them. You got to use topology, right? And then you get an answer which expresses the diffusion of the whole thing, topology included. Topology means the regional anatomy of the network of watersheds and channels. Okay. The convolution is an established method. Sherman, 1932. He was not the first one, but he was the first one that got the credit. That happens, by the way, in the real world. Number two usually gets the credit. Number one, nobody really knows, and so forth. Sherman was definitely number two. Likewise, the Cascade linear reservoirs is at the core of many hydrologic models, among them the SAR model. Now, I should tell you that I do not know what the status of the SAR model is. I know that they never got to GUI. I'm not in touch with those guys. I should, but I am not. So I don't know anybody. I mean, Don Newton died. You know, he was a friend, but I mean, not a friend, an acquaintance. But he died. Not the other guys. I don't know. I don't know exactly what they're doing up there at the Portland District of the North Pacific Division. Portland District, I believe it's called North Pacific Division Portland District. They are the ones that invented the SAR model in the 50s. As a matter of fact, the SAR model is considered to be the granddaddy of all the hydrologic models. They precede the Stanford model. Now, a lot of people consider the Stanford model to be the first model in the US, but that's not true. The Stanford model is dated 1964, while the SAR model is dated 1955 or something like this. So the SAR model is the granddaddy of all the hydrologic models. And it worked really well, and they were able to design all the dams on the Columbia because they wanted a forecasting router model, right? So that's what they had their model. Unfortunately, they got hit by the GUI fever. The GUI fever. The GUI fever came about in the year 1992, 93. When Windows came about, if you remember, you don't remember, you're too young. But Windows came about in the year 1991, 92, Windows Microsoft, which was not the first Windows. It was the second Windows. Prior to Windows Microsoft, there was a system called X Windows, which we used at the beginning, like in the late 80s. Little to be known was that Microsoft was going to come very strong in the next few years and take over the market, and call themselves Windows. And now everybody says, Windows, what is a window? Window is a Microsoft Windows. They took the word. I guess people would say kind of harshly that they stole the word, and that is correct. They stole the word Windows and they used it for their model. So after Windows came about, then everybody they had to jump the bandwagon. So the Army Corps said, I'm going to do GUI, and they switched their HEC1 and developed HMS. And then they took HEC2 and developed RAS. And you're working with those models now, because those two models were developed in character cell form in the year 1968. So it took 30 years, from 68 to 98, to convert them into GUI. Unfortunately, neither the soil conservation or the North Pacific did that. It is my understanding is that they never. It takes a lot of effort to do that. As a matter of fact, I have a story that I told on the web. You know, Professor Ponce got a lot of stories. I met with Arlen Feldman at the time. This is not a good story, but it is a story nevertheless. And you know Professor Ponce. I said to Arlen's a good friend. Well, you know, acquaintance, professional acquaintance. Arlen, I said, are you guys going to release the next version of HEC1 and HEC2? That was in 1995 or 6. And he said, I was there visiting somehow. He says, no, Ponce, we're putting them in the back burner. I said, really? How come? And he says, because we are developing the GUI versions, you know, we're coming up with new models. GUI, graphical user interface, Windows. Okay, good. I understood that at the time. Okay, because we were already using Windows at the time. Not the Windows that you guys use, but the other Windows. Okay, the Apple, which is Unix, by the way. At any rate, that's a long story. So then he said, at the end of the conversation, it was a fascinating conversation with Arlen Feldman. He was the chief of research. He must have retired already. A lot of people that I know have already retired. Professor Ponce still around. And he said, You know, Ponce, in order to acquire the GUI capability, we had to sell half of the store. Oh my gosh, I said, really? I understood exactly what he had said. And I'm not sure you guys understand it. So I'm going to leave it for the end. Maybe think about it. Okay? That's what he said. In order to acquire the GUI capability, we had to sell half of the store. Okay. So let's move on. Effective, effective storm hydrograph. So there's an example in here of an effective storm hydrograph. Then the unit hydrographs. Assume aquí. We're gonna hear an example. We're gonna get an example here. And we use the basin area 432. Why 432? This is the actual basin area that Dot Newton, for some reason, showed or chose to prove his methodology. And since we were picking data from him, we picked a 432. It's a good number. Not too high, not too low. Applicable unit hydrograph duration, etc. The same thing. The basin is assumed to have a relatively steep relief. We're going to do a calculation in here. So if it has steep relief, the Courant should be high. So the Courant is 1. It cannot be more than 2. So 1 is good. And the number of reservoirs should be low. So in here, N2 is good. It's not 1, it's not 3, it's 2. Okay, so then we have the program that generates the dimensionless unit hydrograph in here. Okay, and then the total time in hours, and we have the unit hydro. Then with that, the unit hydrograph, okay, we get this unit hydrograph for the basin that we have chosen, 432 in 1 hour. That's the hydrograph that is calculated. I know this could be confusing, but bear with me a little bit here. So then the Cascade linear reservoirs. With these numbers, C equal 1, that means K is equal 1, because delta T is 1, so delta T over K is 1, C equal 1. Then we use another program which is called online routing, which is this program over here, which I'm going to ask you to run. I'm going to ask you to run this program on a, I don't know what I'm going to do in here. Yeah, it's cool. We got it. Sometimes I have not put that in there. So I'm going to ask you to run this program to generate the Cascade routing. Because I had about 8 programs of routing on my page. These programs that I just introduced to you today are new, but prior to that, I had already written masking of Ganj and this and that, linear reservoirs, so they're all in there. So I'm going to ask you, as part of the homework, to run online routing 8. So that's the online routing 8 now with the Cascade linear reservoirs. Now we also have the convolution, and the convolution can be done in my website with a program also, online convolution. You urge to try that. And we get this. And we get the same answer. Look at this. On 32222, and over here is on 3222223. There's one digital difference in the 7th decimal place. And you all know that the 7th decimal place is where the computer has to fail. So I'm not surprised that that's the way it happened. I'm just totally, my surprise is not that it didn't fail. It is that it's so close. It is amazingly close. That means they are one in the same method, mathematically one in the same method. So we have a discussion in here. Method of Cascade linear reservoirs calculates a composite hydrograph. The convolution with the effective storm hydrograph gives the same composite flood hydrograph, provided the cascades are used to derive the unit hydrograph of the convolution. Once the applicable cascade parameters are established, the cascade and convolution methods give exactly the same results. So now we have a good method. We don't have to do the convolution anymore. We can do the cascade because it's the same. Because the convolution is a little messy and so forth. But in here, the issue now becomes, what about practice? Can we use this thing? Is it just an invention or can we use it? And the answer is yes, you can use it. Of course, Those people that use the SAR method around the world um, are familiar with the method, and they know that they've got to calibrate the parameters. The Brazilians knew it when I was there. I am told that the Mekong people in Thailand or consultants, they're off, apply the method in the Mekong basin, Mekong out there in Thailand. And I don't know of any others, but I'm sure because this was an American method, and it was an old method, an established method in the 60s and 30s, 70s and 80s, it was readily picked up by people around the world. You know, American technology, they pick up the American technology. So it must be that many other applications out there in the real world that I don't really know about. And they know how, from experience, they know how to calculate the CNN. But in here, we're going to tell you something. We're going to say that we can relate that to the geomorphology. The cascade parameters are estimated based on the runoff diffusion properties. The key point here is runoff diffusion. Remember runoff diffusion of the basin under consideration. The runoff diffusion properties depend on the terrain's topography and geomorphology. Steep basin, what's the difference between topography and geomorphology? Well, topography is a term that engineers use to figure out the shape of the terrain, but it has a kind of a tendency to be local. Like you get hired to do a topographic job. I remember when I was young, I used to do that kind of work a long time ago. Geomorphology is more like a global subject that will tell you about the shape of the. So it's like global versus local. Geomorphology is more global, and topography is local. Steep basins have little or no diffusion. That we know for a fact. Conversely, mild basins have substantial amounts of diffusion. The case of zero diffusion is modeled with C equal 2 and N equal 1. We know that. That's a rational method. Conversely, the case of large diffusion may be modeled with C.1 and N equal 10. Now, when Don Newton did his method in the 50s, it could have even been in the 40s, I don't know exactly. I know they published it in the middle 50s. They divided the hydrograph into three parts: the surface runoff, the inner flow, and the groundwater flow. That makes sense. That's exactly the way it happens. You know, the real hydrographs have a long tail. And the long tail comes because of the fact that one hydrograph could be considered to be the unity or the combination of three hydrographs. The first one is fast, that's the surface runoff. The second one is a little bit delayed, which nobody really knows how to calculate. They just kind of guess it in. And the third one is the base flow. And the base flow, we know how to calculate base flow. Base flow has a highly diffusive because it goes through the groundwater. And the groundwater, the formula that operates in the groundwater regime is a diffusion equation that has no convection. The kinematic wave is all convection, no diffusion, and therefore it goes quick, fast, and maintains its stage. On the opposite range, the groundwater flow has all diffusion, no convection whatsoever. So if you put in there any peak or anything, it just diffused and appears 10 years later downstream. Well, not 10 years later. It takes time. Depends on how long it is. We always said when we looked at this that 7 years is what it would normally take water that seeps into the groundwater to show up later somewhere. But that's just a number. It could be 9, it could be 7, it could be 20. But 7 is a good number that we use, by the way, in practice. 7 years. Once the water gets into the ground, it'll take 7 years to show up. So why? You ought to wait 7 years? No. You're looking at the water that seeped into the ground 7 years ago. You see how it works? It's constant. It's a constant flow that is coming out, highly diffused. So Don Newton used 3 components for the hydrograph, and he was correct on this one. The surface runoff would be, for instance, C equal 2 and N equal 1. The interflow would be C equal 3 or 4 and N equal 3 or 4. And by the time you get to the groundwater, you could use C.1 and N equal 10, or even longer. Nothing stops you. If you use C.05 and N equal 50, you will get base flow. You will get a totally diffused hydrograph. You see how it works? Okay. In nature, basins are classified by random diffusion on the basis of the mean land surface slope. Preliminary classification is proposed in Table 6. So look at this here. When the mean land surface slope is very steep, greater than 1%, 10%. 10% is extremely high. 10% you see in places like Peru, places that have high mountains. Actually, in the United States also, but not as high. The United States peak at around 3,000 meters. About 3,000 meters is what? 12,000? No, they peak a little more than that. But in areas like Peru, the peaks are 6,000 meters. Okay, so the Cascade parameters 2 and 1, right? In the values of peak flow, like the rational method values, right here, rational method values, very steep, 2 and 1. Steep from 0.01 to 10. Then you have the Cascade parameters and the values of the unit hydrograph, the generalized dimensionless unit hydrograph. As you can see how the peak starts decreasing to 47%, 22%, 8%, 3%, 1%. And the time to peak increases to 2, relative, 2, 4, 11, 36, 81. So this gives you a range of hydrographs. You got to pick something up. And if you do it once or twice, you run it through and you verify it, you calibrate it, then you're fine. Because then you more or less know what's going to happen. And these systems don't have a way of changing that stuff, by the way. If you change it, changes a little bit, but not a whole lot. So once you pin it down, you pinned it down. Okay, the methods of Cascade and unit hydrograph are shown to be one and the same, and to give exactly the same results, provided the Cascade parameters are used to calculate the unit hydrograph of the convolution. That's a good phrase. In the absence of gauge data, the Cascade parameters may be estimated based on geomorphology. Here, or here. Once the parameters are established, the composite flood hydrograph is uniquely determined by either method. Now, Chow, in his 64 book, which is called Applied Hydrology, he describes the Cascade kind of nicely. He doesn't say what I said here today. He could not have, because we did this in 2009, and he was writing stuff to 1961, 62 to 64. And besides, I already told you, Chow was not a researcher. He was a writer. He was an excellent, the best writer, but not necessarily the best researcher. So he wasn't going to do the research to write a book. As a matter of fact, the book Chow wrote is an encyclopedia. He didn't write it. He wrote only one chapter out of maybe 15. That's the way they do it. Important gentleman gets together a bunch of people to do the work, and he does the lead chapter, and then the other people work on the other chapters. And that's the way it should be, because nobody can know everything. That's a fact. Okay, so I'm done with this now, and I've got about 10 minutes, so we may get there. Okay, so then the next thing we're going to do is we're going to look at practice now. We had a student from Peru. I have an association with several universities throughout Latin America, Mexico, Peru, Ecuador, Colombia, Bolivia, too. Never got to Chile, by the way. Argentina, a little bit. Brazil, certainly. I've been in Brazil many, many times. So this gentleman, his name is Arisa, Luis, I believe, wrote to me, and he said that he needed to finish his thesis or write his thesis. He had done a master's at the university in my alma mater out there, the University of Engineering, and where the smart people are actually. It's very competitive. I think 8% of the people that apply get in, right? So it's very competitive. Everybody gets out of the university is generally supposed to be a very smart guy. So Arisa was very smart, but he did not quite like the suggestions of his advisors. He just didn't like it. So he said, Professor Ponce, can you give me a topic that I could use? So I gave him this topic. I talked to his advisor, whom I know personally, and I said, we'll do this. Are you okay? And he said, sure. So we set up the committee, and I was an external member, kind of. And there was like a committee, normal committee. And he did his thesis. He came over here for 4 months and did his work. Now, I can tell you off the back of the bat that had he not have the online calculators, he would never have done the work in 4 months. but he had the online calculators. And Ariza is a very sharp cookie guy. He was running those calculators at the speed of light, which is the way it should be, by the way. So he finished in 4 months. He was here from January to May, and he finished his job. And this is his job. This is the job that that's right there. That's Ariza, Luis Gustavo Ariza. Okay, so obviously this went into a thesis. There's a thesis out there. He defended the thesis and so on and so forth. And there he is. There's thesis. I'm not going to go over the entire thesis. You are certainly welcome to do it. I don't think you can. It's about 100 pages, something on that order. I'm just going to browse through it. What did he do? Well, he first talks about the SAR method, the unit hydrograph, etc. Right? I asked him to select 10 watersheds throughout California to gather the data and to analyze according to the methodology to GDQH, and figured out what the current number in Cascade reservoirs were based on the data. For that, you had to have data. And it's a good thing that here in the United States, the data is freely available, which is not the case in some countries. Certainly in Peru, it wasn't. I'm told that thinking about it, they already did it because they had to follow suit. Because once the US, about 10, 15 years ago, decided to go free on the data, they figured that data belongs to the people. So if you want the data, you can download it. And that's typically the case. And that's good. That's good. The government should not own the data. I mean, private parties can, because that's why they're private parties. But the government should not own the data. The data is owned by the people. That's why we pay the government, right? Our taxes. So in the United States, the data is owned by the government, and not the government, owned by the people. And you can download freely anything from USGS and all the other agencies. So that's cool. So he was able to get the data. He got his hands on the data. He looked at the unit hydrograph. These are charts from my book, by the way. He got the unit hydrographs. He said, can we pick up the charts from your book outright? I said, sure. We're all sharing stuff in here. Everybody copies nowadays. Sure, everybody copies. Copy is a good word because you can pick up from Google, pick up from here and there. You got to be reasonable and you got to be careful, by the way. But these are my charts in my book. He's talking about storage routing in here. It's a good review, by the way. And all theses should have a good review of the material. The time levels, the linear reservoir constants, because that's what he's going to be doing, linear reservoirs, right? When you get to 2 in here, the C2 coefficient gets to be 0. That means rational method. So for 4, the C2 coefficient is minus. That means the flow is negative. It became unstable. Why did it become unstable? Because that's not a reservoir, because it says that the K is too small. Delta T over K. So delta T is 4 times the K. So that's the K too small. The K is supposed to be a reservoir. It's supposed to be long, not short. If it's too short, then you're basically telling the computer, get that water into the reservoir and kick it out as soon as you can. Throw it into the air, right? And that's exactly what actually happens out there. If you use 4 or 8 or 16, God forbid, you get all kinds of weird, unreasonable, physically unrealistic answers. So then we talk about the Cascade of linear reservoirs over here, and our formulas, and the formulas, our formula is 212, and Newton's formula is 213. And that's the one I've asked you to compare. So you should show that 212 is the same as 213. It's not easy, by the way, but it can be done. Spend a couple hours on it. Maybe, depends on if you're good with algebra, maybe it'll only be an hour or so. Instantaneous unit hydrograph. We need to put in there Nash because he was the inventor of the whole thing. So the 214 is Nash's equation. We needed to put in here the Rodriguez-Iturbe work, the geomorphic instantaneous unit hydrographs. Now these guys, I don't like to talk about people, and sometimes I have to, but these guys are a bit of magicians. They put it in difficult terms and then nobody can understand, okay? But we had to put in there their work because Because if we don't, then people are going to say, why didn't you mention them, you know? But Rodriguez Iturbe had worked on the geomorphic instantaneous unit hydrograph. Now, the CLR method was called instantaneous by many people, and even to this day, they talk about IUH in the books. I never could understand what the heck does instantaneous mean. If instantaneous means reproducible and constant and is the same no matter what, then it's okay, but the word is poorly chosen. You cannot have any instantaneous hydrograph. That would be impossible to handle, right? So I don't like the word instantaneous. Nevertheless, we had to admit it, we had to put it in there because so many very important people are using it. Okay, so and Rodriguez Iturbe worked on what he called the GIUH, the geomorphic instantaneous. So he was really talking about the same thing. Cascade linear reservoirs he called instantaneous, and geomorphic, which is the same thing we're using in here. So we figure we put in here some of his work. And of course, he ended up with all kinds of empirical formulas, which have a tendency to cloud the issue. Like here, look at this. These are Rodriguez Iturbe's bases. 131, pulled out of the air, 0.44, etc. Okay, anytime you see an odd number in there, it's very likely that it is an empirical number and therefore pulled out of data. It's not global like ours is. Okay. The concept of random diffusion, we already know that. That's I think I already told you, we came up with that phrase and we're very proud of it because that's exactly what it should be. What we're calculating as engineers is how much random diffusion are you having. Random diffusion in reservoirs, we already talked about. Random diffusion in stream channels, there's our S-curve. And random diffusion in catchments, I believe we already did this work. I think so. Yeah, we have. I'm not sure, but we'll get back to it later on. Do you remember this graph in here, Andrea? Have you ever seen this graph? I think you have.
Yeah, I've seen it.
Yeah. This is the random diffusion in reservoirs. Meaning, if the rain stops, the reaching the peak will stop also, and it'll come down. So effectively, that has diffused, even though it was not supposed to diffuse, but it did diffuse because of the relationship with the rain. Not the same in a channel. In a channel, you have an inflow and an outflow, and an inflow is constant and the outflow is constant. So there's no way that the inflow is going to finish. If the inflow finishes in a channel, you got something really weird in there. But in the plane, you can. You can be simulating a plane and it runs it runs out of rainfall. Rainfall stops, right? So then we created the concept that there is the runoff diffusion in catchments, but not due to the runoff diffusion, but due to the interaction between the catchment and the rain and the precipitation. And we calculated these numbers. Now, these numbers could not be calculated prior to the work we did here because nobody had a diffusion wave model. They all had kinematic wave models. And the kinematic wave models were not accurate. They were not perfectly accurate. These are perfectly accurate because they are gradient dependent. Okay, and then we added something in here for the sake of history, the Horton formulas, and the general dimensionless, here out of my paper, right? And the methodology, simple storms, calculate the unit hydrograph, calculate the cascade parameters, complex storms. We didn't get into complex storms because it's kind of tough to do, but I asked him to put it in there. In convolution, he talks about what is convolution. This is the convolution. That's the example for the convolution. Inverse convolution is the method that gives you a hydrograph and you reverse the process and try to get the unit hydrograph. Normally, the convolution, you get the unit hydrograph as input and the flood hydrograph as output. But if you only have the flood hydrograph and want to get the unit hydrograph, you can do a reverse convolution. It's very tough. It's in my book. But I asked him to do it. Put it in there for show, just so that they know that you know, okay? A lot of people don't get into this, by the way. So this is the formula for inverse convolution that is in my book, the 3-3. And this is an example for the calculation of inverse convolution. We actually have not done a calculator on this. And you know why? Because I don't think anybody would use it, simply put. Besides, it's tricky because it depends if the data is ill posed, it'll give you trash. So the data has got to be perfect. In other words, you got to have an inflow hydrograph, a unit hydrograph, some rainfall, and get the flood hydrograph. Then you can take that flood hydrograph and reverse the calculation, almost as if you're going backwards, right? But if for whatever reason the measured hydrograph, or rather the flood hydrograph, is a measured hydrograph or a real hydrograph, then it has some nuances in there, then you may not be able to get back to the calculation, just simply put, because the calculation is not strong. What does that mean? It's a very apropos that we should talk about that. Robustness is a characteristic of a method that does not go bad readily. It's robust. The robustness of the scheme. People talk about that in those terms. So this method is not robust if you have a calculation that is a little bit odd. A little bit odd will throw the calculation off completely. Okay, general dimensionless unit hydrograph, we already talked about that, right? And you already seen these graphs in here. They are part of my book or part of my papers. Series of dimensionless unit hydrograph. Now he gets the dimensionless unit hydrograph for C equal 2. You can see very nice. The reservoirs from 1 to 10, right? For 1.5, a little more diffuse. For 1, more diffuse. For 0.5, more diffuse. And 0.02 and 0.1. You can see the 0.1 values are almost to the point where hydrograph is not there. It has been totally obliterated by the runoff diffusion. And then for n equal to 1, oh, okay, this is the opposite. Now, this one was various n's for 1c. This one is various c's for 1n. Just kind of to show the behavior, because this stuff apparently had not been shown. So we were trying to show off in here and show all these things, how they could be done in color and everything. GDUH, this is like a book on the whole method, by the way. It's very good. Many of its parts are a review of what I had just said earlier, but it's a good review. GDA, convolution, etc., etc. These are all charts, the graphs from my calculators. And then the data analysis. The data analysis was all his, by the way. Professor Ponce is very good with theory, but I am not very good with practice because, okay, let's just say, meaning that I don't handle a whole lot of data. But this gentleman, Arisa, was good. He was really good. He's one of the best I have seen. So he was able to handle the data, and pretty quickly he got on top of my calculators, and he was able to do a great job in very quick amount of time, ready amount of time. So he's talking about the watershed characteristics in here: compact ratio, average land surface slope, stream channel slopes, and these are the various watersheds that he chose. Start with Campo Creek. I told him go to Campo because I like that basin. I've studied the Campo basin extensively over the years. And then the other ones, I gave him some pointers. I said, well, you can go here, you can go there. You know the hundreds of thousands of watersheds in California. The question is there data? So you had to pick up the watersheds that are reasonable, have reasonable amounts of data. And he did that. He went to the Whitewater near Mecca. I've been there too, by the way. The Whitewater is the northern tributary of the Salton Sea. Mojave River near Victorville. I've been in the Mojave too, maybe not close to Victorville. Amargosa, not been there. Petaluma, not been there. Russian, yes, I've been in the Russian River. I have pictures of the Russian River. Los Gatos Creek near Coalinga. I've been to Coalinga many times. Los Gatos, I'm not sure. Fresno, sure. Cottonwood Creek near Cottonwood, California. That's north, by the way. Shasta, that's north. The Cottonwood is a common name. We have a Cottonwood Creek in San Diego, by the way. Cottonwood Creek, as a matter of fact, in southeast San Diego County, is a tributary of the Tijuana River. And about 20 years ago, we studied the flood hydrology of Cottonwood Creek. We have a report on that. Salinas River near Spreckles, and Shasta near Montague or Montague. I've seen it spelled both ways. Okay, so he's got the data, he's got the pictures. You can pull these pictures out. These are my pictures of Campo, by the way, because I have extensive pictures of Campo. This one has a history. This is a NOAA NWS rain gauge at Campo, California. This rain gauge, it may not be this rain gauge, but this site has the record of the most intense precipitation in the shortest amount of time. Well, it's obvious. In the entire record of the National Weather Service, it's 11 inches in 100 minutes. So it does not rain more intensely than 11 inches in 100 minutes. If it rains more intensely, it has not been recorded. Therefore, we didn't see it. Therefore, it doesn't exist, right? So from all the gauges that we have in California, and we have a lot of gauges, some of them are local, whatever, but National Weather Service keeps a good eye on these. And this one is the Campo gauge that has the 1891 distinction. 1891? 1891 is very early in the game of having rained 11 inches of rain in 100 minutes. They're saying that a couple of days ago when we had the storm in here, that in some places in the county it rained 4 inches in an hour or something like this. That's what I think they said, if I remember correctly. 4 inches in an hour is heavy, extremely heavy. You know what happened. Okay, so then he went ahead and used the GIS that all of you are familiar with to delimit the basin, okay, the Campo Basin. Note that the Campo Basin goes into Mexico. Can you see that? Right there. It goes into Mexico. The gauge is over here. There's a contribution from Mexico. Right there. And so on and so forth. And he did the calculations. He had the gauges, and he was trying to calibrate. He was trying to calibrate the CNN. And he did that precisely because he already had the hydrographs, right? He had 3 hydrographs. He could do 3 calibrations. And nice hydrographs, by the way. That's a flat hydrograph, if I know one. Whitewater River in Mecca, over here, the Whitewater. This is a picture of mine. That's the mouth of the Groundwater River, or the Whitewater River at the Salton Sea. I was there when we studied the Salton Sea about 25 years ago. We extensively studied the Salton Sea, by the way. We'll get to the Salton Sea later on. Actually, take that back. That is in environmental hydrology, not in this class. We're not going to talk about the Salton Sea in this class. Whitewater River Basin, as you can see, gets into the Salton Sea. Right there, the triangle here is where I took the picture of the mouth of the Whitewater. Right there, in the data, in the hydrographs for the Whitewater, cool hydrographs. The Mojave, I actually had pictures. This is my picture of the Mojave. Interesting, wide. This particular has a history because it had a ford. You know what a ford is, right? A ford is in lieu of a bridge. And just like bridges can fail, not too many bridges fail, but some of them do fail. A ford can also fail. And in the year 2005, the ford in here next to Hellendale in California failed. The ford was gone. There was about 4 or 5 feet of water in this basin, in this river. And the 5 feet of water totally erased the ford. We have several pictures of that. As a matter of fact, I have a collection of pictures which I'm going to post for you, as I always do. I'm going to post it as an addition to this chapter. I'll do that tonight. So we are now getting close to our time, so I'm just going to go over here. You're supposed to browse this paper for what's important. And then at the end, we have several other basins. There's 10 basins in here. 10 basins in here, different types. You can see the hydrographs that he picked up were beautiful hydrographs. Nicely well-behaved hydrographs. And then at the end, Los Gatos and Coalinga, Cottonwood, near Cottonwood. This is in the north of Shasta. It means at the end of the Central Valley, northern end of the Central Valley. Hydrologic and geomorphic, another hydrograph. Salinas River. Salinas River, I think I've been out there. Salinas River, anybody, you can go to San Francisco by land and you run through the Salinas River. Shasta River Basin, model application, So he's now going to identify the parameters. He's going to try to do calibrations from geomorphic standpoint. Very comprehensive work, by the way. So we finish here. Oh, he did one trial in here. It says average is the blue and average measured and predicted with C equal 1.77 and N equal 4. Now, how good could this be? It cannot get any better than this. Hydrology is supposed to have a 20% error or 30%. Here, there's no error. Not all of the rivers are well behaved. Like this one was a little bit off, but we were trying to match the peak, and that's what I'm going to ask you to do in the homework, by the way. Likewise in here, Amargosa River, Petaluma River. So as you can see, this work was a tremendous success. And I could not have done it on my own because, like I said, I don't handle the data. I would need somebody young to do that. And he came around, he wanted to do it, he graduated with honors, and now this was in the year 2017, I believe. I talk to Luis all the time. He just got promoted. Not promoted. He switched jobs and took a better job with higher pay in southern Peru. So he's doing well. Likewise in here, and in here, as you can see, the coincidence is amazing. It's really amazing. And then there's analysis in here, a little bit of analysis. There is a little bit of correlation problem, but there's always like that. Like the one on top is a little bit low correlated, but the one at the bottom for the diffusion number, he defined a diffusion number, and it doesn't matter. The point is that we got 99% of it. We got 99% of it, number of reservoirs, example application, summary and conclusions, and that's the end of it.